Here we go. Good afternoon, everyone, and welcome to our Creo-focused webinar today. My name is Rob Romanowski. I'm the Director of Sales Operations with 3HTI, and leading the demonstration and overview is going to be Paul Dye. Paul is a solutions consultant with PTC's Virtual Center of Excellence, and he is also a applications engineer. So today we're going to take a look at kinematic and dynamic motion analysis extension for Creo. And what I'm going to do is, without further ado, let Paul take everything over from here. So we can see your screen, Paul, and you have the con.
All right, sounds good. And you can hear me okay?
Hear you loud and clear.
All right, thank you very much. And thank you everybody for hopping on. I appreciate the time to get through and talk a little bit today. It's a very interesting topic. It's something that I think a lot of companies get good use out of whenever it comes into mechanisms. A lot of companies might work with mechanisms and not necessarily have it as part of their Creo designs, or might not even know exactly all the different capabilities that we really have whenever it comes to doing these types of designs from within Creo. So ultimately, my goal is to give you a little bit of context into exactly what we can do, some of the different areas that we can work with, design, analyze, get reports on, and hopefully allow you to work that into what you're doing currently. So if it's not something, definitely something that and look to expand upon there as well. Wait, and Rob, can you still hear me? I'm not sure if
I hear you loud and clear, my friend.
Okay, and you can still see the screen. I think
yes.
My sharing got a little screwed up. All right,
That's
awesome.
Okay. No,
just making sure. All right. Awesome. Well, then I'm going to go ahead and just jump right into it. So one of the things I like to do before I go through and explain all the different capabilities that we work with from a mechanism standpoint is some of the areas that we really look to use them from within and what it looks to help. So looking at a design perspective, a lot of the models that you might work with, they don't move. Maybe it's something like a building or something like that. That's fine. You can put parts together, say this one's fixed on top of another, and that's really the way that it works out in the real world. But for a lot of different designs that actually do move, most designs that we work with have some sort of moving component to them. You need to be able to take that into account. And it tends to add in complexity. It adds in a lot of new challenges that traditionally CAD isn't very well equipped to deal with. Your CAD designs work well on a computer, but that's not the way that it works out in the real world. Because it's still all, first and foremost, a virtual design that you're working with. Your engineers are still assembling things. If you're doing that from an assembly context and you're working with mechanisms and using fixed constraints and hard dimensioning everything, you're probably missing out on some stuff, right? The truth of the matter is you don't just have these parts sitting on top of one another. You have things like pin joints, you have sliders. These all have movement from one part of the assembly to another, and you're able to take that into account. And really the best designs actually take these mechanisms and work them into part of that design process in of itself, right? And takes part in design exploration. You're trying different things out and ultimately working towards a better design and doing that right from within Creo. Another thing that a lot of people do to avoid that is just build out a prototype, and they do that to figure out if a component's going to work right, to fit and function. And if you figure out something doesn't work, then you build another prototype to test it, and then you build another one, right? Just because you're trying to figure out a certain linkage or piece of the design, figuring out a frame, what sizes that you need for all these parts. Well, that's something that takes a lot of time, a lot of money to do each of those. And ultimately, it's going to give us something that works. It's not necessarily going to be the best design possible with that as well. So that's what we're trying to do, is really going to try to get to the best design out of that as well. So looking at all that, we have different solutions from within Creo to be able to work with these types of designs. And there's two areas I'm going to cover first and foremost. So first area here is going to be with our mechanism design capabilities. This is something that comes standard with every Creo parametric license. It's really our tools right from within Creo for
Hey, Paul. I think we just lost Paul for a moment.
All right. Sorry for any interruption there. A little bit of connection weird with
Hey, it happens
the
every
Zoom
once
meeting.
in a while.
It does. It happens with Zoom, Teams, you name it. I've seen it time and time again. So I think we should be good to going forward from here now. Right. But as I was saying, we have two different sides here. You have mechanism design and then mechanism dynamics. So mechanism design, first and foremost, we're looking at mechanisms. You're simulating them, looking at the ranges of motion, looking at interference, and essentially just integrating all those capabilities into your standard types of models and assemblies. So that's the first half of this, and then we're going to take a look at the Mechanism Dynamics Option, or MDO. So this is an extension that's going to give you extended capabilities to design and test the mechanisms that you're working with and put them under real world stresses. So it's simulating the forces, accelerations, and the moving components, and taking into account influences like springs, motors, friction, gravity. So all that's going to be a part of that mechanism dynamic side of things. So let's go ahead and first and foremost start into talking around mechanism design here. So first and foremost, looking at the ability to define your mechanisms. So not just putting things on top of one another, but defining how they're going to work in the real world. So using things like pins, sliders, ball joints, gives you the ability to build out components for these types of specific functions. And once you have these components put together into a mechanism, then you can run analyses. You can drag components around, you can apply motors to drive them over a certain time frame. So not just the shape and the size and the shape of the models, but have them in motion and see it as that actually is going to relate into the design of the models that you're working with as well. You really want that to influence even the geometry that you're building out around that. And everything that we're doing is still going to be right from within Creo Parametric. It's just something that's going to be available at the top of your screen for defining all of this. Gives us all the different capabilities that you have available to us right in the assembly. So completely integrated there. And all the actions that we're going to take here are going to be real time. You can drag components around based on how your design's being built out. It's going to move everything around accordingly. One thing that this is going to involve as well is what we call interference detection. And if you have a prototype built out, it's probably a bad time to figure out that there's an interference. It's much better to be able to do that simulation right from within Creo. So you can take the model through its full range of motion, see if there's any issues in that front. Definitely something that we want to put into part of that process. Area claim and creation of motion envelopes. This is another great feature that we work with oftentimes inside of mechanism design. So you can look at the area that a part has capabilities to move around from within. So you can go ahead and build that out and visualize that from right from within the assembly. Make sure that you don't have different parts moving into that space. Another area here that we work with is trace curves. So as the part's moving along its path and its direction there, what you can do is define a curve along that path. It really helps you to see the extent of that movement. You could build around it, build off of it, a lot of different options that you have in that sense. And everything that we go through and build and analyze, it can all be saved. These pin joints, ball joints, they really just become a part of that assembly definition. It's not a separate thing. It's not a separate world that you have to go into. It just simply gets saved in with the assembly. And it's something that you can reference back to later on and continue design off of. So that's really just a standard type of look at what you would be using from a mechanism design capability standpoint. So building out the designs and how they're going to work out in the real world. But from that point, what happens as you start to take into account the forces. So this is really now where mechanism dynamics is going to come into place. So anywhere that you could have things breaking in the model, let's go ahead and take some of these other variables into account and look at it from a forces standpoint. So let's go ahead and use all these motions that we worked with from a mechanism standpoint, and now let's simulate those forces created by the different components moving. So we're going to study them, look at them, make sure that they're all going to work correctly. And this is now from within this extension, taking into account real world behavior and building that into the design. So here's now looking at springs where you can define the pitch, the strength, the size. Creo, the system fully understands how that works. It understands things such as stored force, release force, bounce back. Works very similar with other mechanisms, not just springs. We have a few different ones that we could define from within there as well. And really now doing true kinematic analysis, taking into account the position, velocity, acceleration, put that all into the context of your parts that you're building out. And there's a lot of different features and different parameters that you can take into account with that. Whenever you have different springs or dampers or contacts and friction all happening, what types of forces are you going to get along with that? So how is that all going to come into play there as well? And just one moment, let me go ahead and get set back up here. Yeah, sorry about that. It seems like, yeah, sorry about that. All right, so again, everything that we're going to be looking at from a mechanisms dynamics perspective is going to be taking into account real world behavior. So all these things like springs, kinematic analysis that you're looking at from that perspective. A lot of different features and parameters that we're going to look at. So all that's going to happen, see how that's all going to come into play. And one of the big things about this is that the dynamics option is doing all that work for us. So whenever it's done, being able to share off different graphing capabilities, you could take a look at what the torque is on a certain head at certain positions, what's the acceleration, the velocity, anything that you need to check from that perspective. Looking at things such as the reaction forces they're going to get with the different loads and the torque, you can go ahead and graph all that out. And once you gather all that information, we have different options for sharing them off. You can share animations of your different dynamic capabilities, tabular outputs, different options from that perspective. And one of the other greatest things about this is really integrating this into the different steps of the process beyond this. So based on the types of forces you're going to get, you can go ahead and take them over into your different simulation tools. So you can take them over into Creo Simulate, Creo Simulation Live, Creo Ansys. That's where you can go through and start to do things like structural analysis or modal, thermal, things of that nature. Also works well with what we have in our behavior modeling extension. So if you haven't worked with this before, this is a tool that can help you to see, based on the forces that you collected, exactly how thick a particular section might need to be. Or even the other direction, you could go through, look at it more so from an optimization perspective. You can see how thin you can make a certain part, but still stay within a certain factor of safety. So either way, behavior modeling is something that can be integrated in with what you would do from a mechanism perspective. Works over with MathCAD. If you don't use that, digital engineering notebook for doing your different calculations, managing your design intent. So if you're doing calculations there, or you want to push some of the results and document over in your notes, you can go ahead and do that as well. And at the end of the day, we're doing really virtual product analysis. So take all these different factors into consideration, really start to build towards a more optimal design overall. All right, so with that, I can go ahead and now switch over into our Creo environment. So I can give you a little bit more of a visual perspective of what some of these different things look like from within the context of Creo. If you have any questions as I go along here and work through some of these different spots, definitely feel free to drop that in, and I can adjust that as we go along here as well. So I'm going to go ahead and jump into the model that we have here from within Creo. I'm going to be working on this assembly that we have for a turbine system. A lot of different components going on from within here. So let's go ahead and take a closer look into some of these in particular. So first thing, let's go ahead and hide this overall structure assembly that goes around this whole thing. And let's just look at the different mechanisms that we have here. So we have the blades, we have some different supports. That's all attached to a door that we can see up here at the top. So let's go ahead and pull up the first model that we want to take a look at here. This is going to be the linkage to this door assembly. Open up the subassembly for that. Now, this is a hydraulic dampening linkage. So it means that these two centerpieces here, they're going to move against one another. So looking at how this is assembled, typically you might do just a coincident along the axis or a concentric along the faces, maybe a third coincidence to have it all the way in, typical way of doing assembly work. But now it's kind of just stuck there, right? Maybe you could do a distance mate instead to specify how far in or out it typically is, but that's not taking into account what's happening in the real world. You can really go as far or short as you want it there. So what I'm going to do is delete that and instead use a slider constraint. So that's really what's going to be happening here. So with this, the slider is centered, it's aligned, but what we can do now is put translation constraints on this as well. So maybe to do this, we could use a plane that we have here, just tell the system that it's going to align with the face on the edge of the part here. So what that's doing is giving us really the same type of constraints we had before, but now it's going to be useful for us going forward. We have different values, different parameters that we can go through and apply to that slider. So what that allows us to do now is go back into the full linkage here, and you can use your drag components feature, and it's going to work just kind of how you think it is, right? It's going to move right along that axis through the middle of those two parts. Problem is it's still moving anywhere that it wants, but that's one of the nice things that we have here with this slider constraint is the fact that you can go back in and put some minimum and maximum limits on that for where that component can move. So maybe the minimum will be at 0, right up along that datum plane, and then the max will be right at 30 millimeters. So again, really putting this different design intelligence into the model. All right, so you can see now back in this full linkage, if I want to take and move my cursor even outside of the bounds of that, it's not going to move outside of the bounds of where we define for it, but it can go anywhere from within there. And same thing over here with this clevis. So right now it has just a couple coincidence mates. It's not really doing what you probably want it to do. So instead, what we can do is delete the standard constraints that we have here. And let's use another one of the connections that we have laid out in our different lists. So you can see you have a lot of different options whenever it comes to that, depending on whatever your scenario calls for, whatever particular connection that you're working with. In this case here, let's go ahead and use a pin joint and basically say that we want to align that pin to a certain axis. All right, and now can only move up and down from within there. So with that, we can go ahead and define the translation of that pin joint. There we go. And we're good to go there. So now we have a real life pin joint. The system understands that behavior. All the other components move right along with it. So anything that's meant to be fixed, you can use your standard constraints, but if it's intended to move, we can instead use these different mechanism constraints along with that. All right, so what does that mean back in the context of my overall assembly? Let's go ahead and regenerate for the changes that we made here and go ahead and look at the overall assembly. So if I want to move that turbine, how are all the other components going to react? Now, based on how I define that linkage and the pin joint, we can see how everything's going to move around. Kind of seems like it's moving as we intended it to. So what we also can do here is work with the idea of snapshots. At particular moments in space here, we can take a snapshot and remember this certain configuration. So right now it might be closed, so we can go ahead and give that a name here. Go ahead and call that closed. And we can do multiple as well. So maybe you want to drag it open and take another screenshot here or snapshot. Easy enough for that one, just call it open. What you can do from that point is then toggle between those different snapshots, allows you to set the assembly however you need to position it from there as well. It's a nice capability that we have in that sense. And let's go ahead and add in a little bit more intelligence here. So let's open up the assembly for our actuator. In this case, this is going to be the piece that pushes this whole thing open. It's a hydraulic piece. So maybe we've gone through and already put in a slider joint like we saw with the earlier linkage. Now it's moving the way that I want, but instead of me just dragging it open, I want to define a mechanism for that piece. So here, using the mechanism design capabilities, we have all of our different features for defining and analyzing the mechanisms that we want to go through and create. You can see we have a dedicated model tree for our different mechanisms, all the different conditions and the settings that we might need to work with there. In this case, let's go ahead and use a servo motor. That's what I want to use to move this piece out a certain distance along a particular axis. Now to do that, what we're going to do is apply a velocity motor. You can go through and work with this, change the definition to either the position or the velocity or even the acceleration to go ahead and define that. All right, a couple other things that we can go through and define there for that as well. Now, maybe for this one, we can keep that at a constant magnitude. So just give that a value. It's something that we could play around with later. And the idea here is now, instead of me just dragging things around, what I can do is set up an analysis to do this. So what this analysis does is it takes the mechanisms over a certain time frame using certain drivers. In this case, let's go ahead and use the servo motor that I went through and defined with that. Let's go ahead and let this run here. It's essentially going to define a motion across time. And again, you can have as many of these mechanisms as you want to do that. And it'll take a second here to take that through its range of motion. There we go. After we've gone ahead and run that analysis, the system would then tell me if there was any issues. In my case, we're good to go. And once it's run, you have the ability to play back through that analysis. You can take that, look at it, you can speed it up or slow it down, or if you wanted to zoom in on a particular area, you could look at all of those different things. Even if you wanted to capture an animation of that, say this is something that you want to share off with a colleague for that animation, also very easy to do. Right. I can also go through and take different measurements for the different values that we want to see here. So for example, what's the measurement from pin to pin as we move along that analysis? Let's go ahead and take a point that we have here at the top of the clevis. Just go ahead and select on where we want to move that between here. And then we can see at different time frames exactly what that distance is. So that's a good look at how the analysis and the motion works on a particular subassembly. And again, we can go through and look at this from the context of the entire assembly if we'd like to as well. Let's go ahead and see how that process is going to look with all these different components that we're working with like we saw before. And just like we did for the previous example, we can go ahead and set up an analysis over a given time frame and then apply that same actuator motor that we went through and defined. So we just want to tell it where to start from. And what it'll do is run through that full range of motion until one of the constraints that we have defined in our components essentially is going to run out and tell that analysis to stop. Let that run through for a second. There we go. And once it stops, you can go through and look at the different values. You can take measurements of the things that we're concerned with. Maybe in this case, I'm interested at looking at the angle of the hinge. I want to see exactly how far it's opening at that point. Or we just take that, select on the axis that we have of interest. Go ahead and define that for a hinge angle. There we go. Right. And now you can take that hinge angle, measure it through its range of motion, and then from there, give me a graph of it. So it looks like it's going to actually pull in a little bit before being released. So is that right? Is it wrong? Well, again, you're right from within Creo. You can simply go through and work with it, change it up just as fast. All right, so let's go ahead and close that assembly back up here. And I want to go through and add in a little bit more complexity. So let's look at this right down here at our latch. So this latch is actually a cam type situation where we want to grab the outside surfaces of that hook, the surfaces of the pin, and I want to enable liftoff, which means whenever we go through to move that pin, the latch has to get out of the way. So really starting to go through and apply some intelligence here. So my components here know to move out of the way right up into the point where it's clear. And this can have an effect on all the rest of my mechanisms as well. So how far can things move? Is there going to be an interaction between the different parts? And once we go through and set all that up, what we can do then is rerun through the analysis and see how it's going to work as we start to change some of that definition here as well. So go ahead and take a look at what that's going to look like here for that cam. Go ahead and run that back through. And you can see as it's moving through, the latch moves out of the way just fine. Maybe it looks like we actually have to add in a little bit of a limit there, but that's quick and easy to do as well. So now you could go back through any of the points of the analysis, rerun, look at that. Another useful thing that we could actually do here, like I mentioned earlier, is use what we have in our trace curve capabilities. So suppose at the bottom of that pin where it's going through is very important to you. Well, I want to make sure that it's going to clear something. Maybe I even want to go through and build around that, like build a slot or something, for example. Well, after we've run that analysis, we can then generate a curve. So it's going to follow right along that path here. It's easy to go back in and inspect it. So now what I could do is go build off of that curve, something like a follower or a slot for that pin, or just go through and build out some other geometry to make sure that it's not going to interfere with that. So everything that I work with there is all going to be part of our mechanism design capabilities, all going to be standard from within Creo Parametric. So now the other piece of this as well is going to be more so, go ahead and open up a part that I can go through and explain a little bit more into the other half of this, which is going to be the dynamics option. So not just the motion and how things are going to move, but let's go ahead and start to consider some forces along with this as well. Work back here with our actuator. So maybe instead of a servo motor running all of this, maybe this one is actually going to be spring loaded. That's oftentimes how these actuators are built. So with that, there's going to be a few more things that we have to consider. So let's go ahead and get this set up here. I'll start by turning on the different endpoints. I want to go ahead and add in a spring between those two different endpoints. With this, you have options for the strength of the spring, you have the uncompressed length. The system actually goes through and builds me a spring right on top of that. And this isn't just some static piece. You have a lot of different options that you can change for this, for a diameter, how you want it to look. So whenever you take that and you start to move the actuator around and drag some things, what you'll see is that the spring is going to be reactive towards this as well. So let's go ahead and use that drag components again and move this. So it's going to go through and compress and uncompress, just like a spring would in actuality. And whenever it's doing that, it's applying forces. So with that force, you can then utilize that over in your analyses that you want to run. So it's going to create an entirely new scenario for the assembly that we're working with. So now instead of that servo motor pushing the door open and that entire assembly open, let's go ahead now and replace that and use the spring that we built. So again, it's going to be the same general interface for setting up that analysis. You can lengthen or shorten up that time frame. And let's just go ahead and see what happens here. So you can see what that motion looks like. We can add in more complexity if we'd like to, because with a spring like this, it's not just the compression. You also want to take into account things such as friction. There's a lot of different parameters that you can go through and change with this. Maybe for here, we want to add in a coefficient of restitution, essentially just allowing our spring to reach a steady state by the end of this motion. And then from there, we can see what the effect of that restitution would have on the analysis. So quickly go back through and run that analysis. And taking a look at this, we can see that it's going to have an effect, right? At the end of this uncompressing, it actually rebounds a little bit. It's due to the different parameters that we changed. And once we have that playback, you can go through, you can see any time slice, slow it down, share off an animation of that. And we can still use our analysis to take different measurements as well. So we can go through here and look at the position, for example, if we're interested in that. But now with the new spring system, we can see how that measurement changes, taking into account the new forces that we're working with. So I'm looking at the graph here, we can see the initial uncompressing is fairly non-linear now, and we can see that it bounced back at the end of the cycle there as well. And then the end is going to settle out into that steady state. Right. So with that, we can go ahead and move on and do the same sort of thing, but instead of position, maybe now we want to take it to loads. So see what that looks like. What are the loads going to be on that spring? We can go ahead and take that analysis, we can graph it up, take certain values from that, share it off. It's really just that easy. So once you're happy with the analysis that you've gone through and run here, we could take a look again what that's going to do in the context of our full assembly here as well. All right, so we have the spring inside of our system here. We can go ahead and rerun that analysis. Let's go ahead and remove the servo motor that we had from before. You don't need that now that we have our spring added in. And let's go ahead and rerun that. All right, so looking at the animation now, the spring is the one that's forcing that latch open, and after that is pushing the entire turbine assembly out there. And the next step would probably be to make that latch as the starting mechanism for that process. But again, as we want to go through and work with that analysis, we can take measurements, a lot of different options that we have there as well. In this case, let's go ahead and look at the net loads that we're seeing on our spring. One other feature that we can work with as part of this as well is the ability to display different arrows right along with the source of those loads. So what it's going to do is give us information on the direction of the load and the relative magnitude with it. It's going to make it very visual for us to see this. We can also see the graph of those different loads of moving the whole mechanism, how those are going to change over a certain time frame. And not only just graphing it, but whenever we do the playback, we can go ahead and show those spring loads as well. Let's go ahead and play back through this animation here. There we go. So we can see as it's playing through this animation, the direction is going to be changing and the relative magnitude is going to be changing as well. And it's very visual, right? You can clearly see as the mechanism is functioning exactly where those max loads are occurring, understand as how they're changing. And now really starting to understand the design behind those mechanisms and also some of the dynamics that are driving that as well. All right. So now final step would likely be now to take all the different connections and the forces that we have and use them over in our simulation studies. So here, let's go ahead and select on the piece that we want to simulate here. Let's calculate the loads at the start, the end, look at some of the maximum loads, or even just at particular points in time if we'd like to. There's some different options that we have in that sense. Maybe we're going to look at, at 0.5, what are the loads that are hitting that particular part of the assembly? And you can see some of the other listed out options that we have for the different loads, connection forces, moments. You can pick and choose exactly which ones that you want to use there. And once we have that, we'll take those loads and export them out. And now they've been stored into the model, just as a piece of this essentially. And really to see what you could do from that point, let's go ahead and open up a part of this here. And let's open up over in Creo Simulate. So if you haven't worked with this, this is one of our FEA tools or our analysis tools that we have in Creo. And we can see those forces that we have from our mechanisms. Very easy, go through, retrieve them, and work with them. So it's really taking us from end to end here. We designed the part, we put it into motion, apply different loads and forces. And after we study those forces, we can take them over here into our simulation and set up whatever situations that we're interested in. So with this, let's just go ahead and run it through a pretty quick standard static analysis using those loads that we brought in. Obviously, a lot of different capabilities that you have over here in Simulate, but really just want to go through and show the idea of going from start to finish. All right, let's take a look at the results that we're looking at for that basic type of analysis. So using those loads, we can take a look at different values that we're interested in. So we can see what's happening for the stress on the model. We can take a look at the displacement, even animate on those, as you can see there as well. So really go through and interrogate the model even further from that point. That's the process that we have of working, and really the ideal way that we have of utilizing mechanism design and the mechanism dynamics. It's all something that we can have fully integrated and part of that process as we're going from start to finish. All right, so that covers really everything that I wanted to go through and show there. Again, if you have any questions, feel free to drop those in. And just as we're wrapping up, if you do have any questions, I can go through and kind of just summarize some of the main things that I went through and showed today. So just some of the main benefits that we have of working with these different mechanism tools is the fact that we're doing our design work all right from within there and starting to really analyze the designs at the same time. And we're doing more so virtual analysis to see what's happening in the context of the assemblies, getting more insight, using that insight to drive the direction of your designs, still doing that all parametrically. Really helps for things such as design reviews, for example. It's one thing to actually just look at the design, but if you can see how things are going to move, what it's going to look like in motion, it's going to be much more clear to see that design intent, and overall reducing some of the costs that we have around the development by creating more so virtual prototypes. So you can figure out, where there's going to be issues there right from within the CAD environment, really cut down on some of the issues in the rework that you might have out in the real world as well. All right, so that covers basically everything I wanted to go through and show. Again, a couple main differences that you have between the standard capabilities for mechanism and some of the dynamics options, but again, really all just part of that same process as well. And with that, I can pass it over to you, Rob.
Awesome. Thanks a lot, Paul. I appreciate it, buddy. So that's going to conclude our webinar for today. So we're going to be back on the 4th because next week is PTC's kickoff. So we will be focused in meetings all of next week. But look out for an email for Wednesday, November. I'm sorry, I'm looking at the wrong calendar. Wednesday, November 1st, where we're going to take an introduction and overview to PLM Windchill, Windchill PLM rather. Anyway, we have a question that just came in. Can the mechanism design be combined with the skeleton model within the assembly?
Yes, so either way, essentially. So one way that you might do that is use some of the motion to define your skeleton. It's definitely one way that you could do that, or vice versa if you have some type of skeleton model set up where you want that to use and drive your mechanisms. That's also definitely an option that you have. So we definitely see some different customers doing that type of work. So if you do have your skeletons model set up, you can incorporate that into what you're doing from a mechanism perspective.
Cool. And we got a request for the last slide with the different capabilities.
Here we go. So this is just kind of laying out some of the different options that you have in the sense between your standard mechanism design capabilities and Creo. It's just part of your tier 1 license of Creo versus what you're doing from a mechanism dynamics option. Really, the main difference that you'll pretty much see as part of this is whenever you start to take into account your forces. So that's going to be the switch over from your standard mechanism capabilities, looking more so at the motion, like you can see there, versus what's happening now that you're starting to take into account the different forces as part of that motion.
Awesome. Cool. Good questions. Thank you, everyone, for being on today, and we will see you again on November 1st. And enjoy the rest of your week and the weekend. Take care, everyone.